Okay, hello guys, those joining us online. So we've been talking about these polar bonds, bonds where there's a significant difference in the atom's ability to attract electrons, a significant difference in the electronegativities, and we said from a range of 0.5 up to 1.9, the bond became polar. If there are polar bonds in the molecule, it could result in the molecule being polar. And all we mean by polar molecules is that we find more electrons on one side of the molecule than the other. And so one side of the molecule is electron enriched, whilst one side of the molecule is electron deficient. A little bit like needing an even distribution of weight in a boat when you're out to sea. If the weight distribution isn't even or close to being even, then we could see the boat being tipped up from one side of the boat. So an uneven concentration of people is kind of like having an uneven concentration of electrons on the molecule. And this makes the molecule polar. Now the easy ones to understand are when there are exactly one bond, there's one bond in the molecule which is polar covalent. One bond which is a dipole bond because of the difference in electronegativities. That always makes the molecule polar. Let me get my little drawing bit up here so I can constantly see it. So if we think about a molecule like formaldehyde, CH2O, for the hydrogen atoms, their electronegativity is 2.1. We put this in black, so it'll probably stand out better. 2.1 for hydrogen, 2.5 for carbon, and then 3.5 for oxygen. So remember, it's got to be 0.5 up to 1.9 to be significant. And so for carbon to hydrogen bonds, that's a difference of just 0.4. So the carbon to hydrogen bond is non-polar, which I'll write very badly there. Carbon to oxygen, that's a difference of 3.5 to 2.5, difference of 1.0. That bond is indeed polar. And so we draw a dipole arrow alongside the bond. Remember, the arrow is always pointing to the more electronegative element. It's almost as if we ask, well, where are the electrons heading? Where are the people in the boat heading to? They're heading to this end of the molecule, up towards the oxygen head, which is further enriched with electrons because of those lone pairs. So in this whole molecule, the majority of its electrons are tied up in this oxygen head of the molecule. So one side becomes electron enriched and delta negative. The other side of the molecule becomes electron deficient and becomes delta plus. It's like milder, weaker forms of ion charges that we saw in chapter 3. So with one bond being polar, the molecule is always polar. Likewise with the chloromethane, again the hydrogen, that's an electronegativity of 2.1, 2.5 for carbon. Electronegativities are things that you just be given. So for the chapter 4 exam, you'll have access to a table of electronegativities. You would never have to memorize these values. Chlorine, 3.0, a difference of 0.5 from chlorine to carbon. So again, we've just got a polar bond. So the electrons have been drawn towards this chlorine head, which is further enriched with these lone pairs of electrons. So here's our electron-enriched side of the molecule in red, and our relatively electron-deficient side of the molecule in blue. And so we create a polar molecule once more. Molecules with exactly one polar covalent bond will always make for polar molecules. Like the ship is always in danger of tipping over if everybody's heading to one side of the ship. Similarly with the chloroethane, again 2.1 for hydrogen, 2.5 for the carbon, a difference of just 0.4 or a difference of 0 for the carbon-to-carbon bond itself. So these bonds are non-polar, but we don't see an even distribution of electrons in that carbon-to-chlorine bond. The chlorine, more electronegative, as we saw before, is drawing the electrons to this tip of the molecule, making this side of the molecule more electron enriched. And so we've got a delta positive side and a delta negative side. We've polarized the molecule with that one bond. Likewise with the hydrogen fluoride, that one bond polar because of the difference in electronegativity, 2.1 to 4.0. And it's just a sheer difference, the bigger number minus the smaller number. And it's always interesting to note that as the differences in electronegativity get bigger, the polarity of the bond gets greater. So bonds with bigger differences are more polar than bonds with smaller differences. Let's try an example, drawing a Lewis structure and determining if the molecule is polar. Any questions at this stage, by the way? This is kind of what we might have slightly gone over on Wednesday as well. Oh, of course, I put my drawing package up here. There we go. That's better. So if we look at an example here with the, let's see, Si2H3Br. Again, we can work out our electron count just by looking at the periodic table. And so for silicon, from its position, if it wants to complete its shell like argon, it needs 1, 2, 3, 4 more boxes, 4 more electrons to complete its shell. So we expect it to form 4 chemical bonds. And from its position, we count sodium, magnesium, aluminium, silicon, 4 boxes to reach it. So it has 4 electrons. For the hydrogen atoms, it's the first box in the first row. It has 1 electron. And to reach helium, its target, we need 1 more box, the helium box itself. So it needs 1 more electron. So we expect it to form 1 chemical bond. With the bromine, it's a little bit trickier because although we're in the 4th row of the table and therefore start with the 4th shell, of course we see that transition block for the first time. And that transition block from scandium, let's see, just lose a thicker pen. Scandium, oh, I didn't want that. Let's switch to red. So from scandium all the way up to zinc, those boxes signify electrons going into the D subshell, the 3D. We said this in chapter 2, the D block is always 1 behind where we are for the S and the P. So while this is the 4S with 1, 2 electrons, and this is the 4P with 1, 2, 3, 4, 5 electrons, that D subshell is part of a shell which is buried beneath. So for valence electrons, the bromine has 1, 2, 3, 4, 5, 6, 7, and it needs 1 more to complete its shell like krypton. So we expect 1 chemical bond. The goal is still completing octets, just as we saw in ion chemistry, but they're sharing electrons to complete those octets. So for our molecule here, let's go back to black. So Si2H3Br. From the table, we saw that was 4 electrons for a silicon atom to reach it. So that gives us 8, 1 electron from each hydrogen. So that gives us 3, and then the 7 electrons for the bromine itself. That gives us a total of 18 electrons. Should always be an even number for that electron count. If you get an odd number, something's gone wrong. And as we saw, silicon needs the most electrons, so it should form the most chemical bonds. So we can put it jointly at the center of the molecule with the other silicon atom, just as we did with hydrazine and the peroxide when we looked at them the other day. So we're down to 16 electrons. We'll use the remaining electrons to connect the other atoms to the central pair. So 2 bonds for each of the 2 silicon atoms. That uses another 2, 4, 6, 8 electrons. This takes us down to 8. We'll use the remaining electrons to complete shells. Of course, the hydrogens have 2, like helium, so they are happy. Bromine, of course, needs 8 as it tries to fill its 4s and 4p subshell. So 2, 4, 6 and the bond 8. That takes us down to 2. And the last 2 we can put on the silicon atom, or one of them. Don't split them up, just put them on as a lone pair. And then for that last atom of silicon, which still doesn't have its octet, because it sees just 2, 4, 6 electrons, we could either use a lone pair from the bromine to complete that octet, or use the last lone pair that we designated to the silicon. But just as we chose silicon as the central atom because it needed the most electrons, it's still the atom which should form the most bonds because it needs the most electrons. So we can redesignate that lone pair as a bonding pair or between the 2 silicon atoms. There's my eraser. So there's a silicon to silicon double bond. Now the hydrogens have their duets and the bromine and silicon atoms have their octets. Looking for the shape of the molecule, we have to take a designation of shape from one specific point in space. So if we look at the electrons around the silicon atom, it sees 1, 2, 3 bonds. Remember those double bonds we count as one single entity. Likewise with its neighboring silicon atom, 1, 2, 3 bonds around it. And with 3 chemical bonds, our shape is trigonal planar every time. Not to be confused with trigonal pyramidal, because trigonal pyramidal has a lone pair of electrons on the central atom. Okay. Trigonal planar with a bond angle each time of 120 degrees. Thinking about the polarity of the molecule, or potential polarity, we have to compare the electronegativities. Remember, you would just be given those in an exam. For bromine, the electronegativity is 2.8. For silicon, it's 1.8. And for hydrogen, it's of course 2.1. So from the hydrogen to silicon, the electronegativity difference is just 0.3. That's not enough for a bond to be polar. Remember, our range, inclusive range, is 0.5 up to 1.9. Anything below that is covalent. Anything above that is ionic. And 0.5 up to 1.9 is a polar covalent bond range, what we sometimes refer to as dipole bonds. That's more of a physics term. So that's non-polar. Likewise with the silicon to silicon bond with no difference, that's non-polar. But the bromine to silicon bond, 2.8 to 1.8, that's a difference of 1.0. Why is everybody suddenly trying to contact me after 0 text all morning? Let's shut that off. Sorry. difference of 1 point, oh, it's a polar bond. Remember that dipole arrow points to the more electronegative element. So it's almost like a bond in its own right, going from one atom to the other, parallel to the polar bond. And then just towards the end of the arrow, we put that little tick or cross through that end. And then that way, as we look at the end, it looks like a plus symbol. That's our electron deficient side of the bond. That's our electron enriched, which would give a delta negative charge. While the silicon, oops, a bit cramped here. We take out some of this stuff. Well, the silicon itself would be given a delta plus symbol. So a majority of the electrons at this point in the molecule are being drawn towards the bromine. And so we're particularly electron enriched in this one corner of the molecule because of the polarity of the bond. Again, with one bond being polar, the molecule is always polar. Any questions about that one? We're doing okay? Very quiet, very polite this morning as usual. Okay, let's clean this up and go to the next one. Okay. So the tricky examples are always when there are multiple polar covalent bonds. Because then we have to ask the question, do the bonds work together to send the electrons to the same side of the molecule, making the molecule polar? Or like maybe people in a boat heading to opposite ends of the boat, if the electrons are moving to opposite sides of the molecule, they would cancel out each other's effect. And so we would get a molecule which has polar bonds, but it isn't a polar molecule because of that cancelling effect. Let's look at ones which have polar bonds, multiple polar bonds, which are still polar. Good example of that is something as simple as water. So looking at the Lewis structure, we have got the oxygen, which is much more electronegative than the hydrogen, of course. Electronegativity of oxygen, as we've seen, is 3.5. Electronegativity of any one hydrogen is just 2.1. That's a massive difference of 1.4. It's never positive or negative, it's just a sheer difference we're looking at. And so we do indeed have those polar covalent bonds, the electrons being drawn towards the oxygen atom. Now, if water was linear, then those two polar bonds would be butting heads and cancel out each other's effect. But they're not cancelling out because the molecule is non-linear. Those lone pairs of electrons on the oxygen bend the molecule into that V shape, that non-linear shape. So if we treat the molecule like a triangle, all the electron density is being focused up on this top end, this apex of the molecule of water. So one side of the molecule is electron enriched, the oxygen head, and the hydrogen feet are the electron deficient side of the molecule. So there's a polarity, the sum of its vectors going through between the two hydrogens right through the oxygen atom. So the polarity of the molecule becomes the sum of its vectors. Looking at a molecule like dichloromethane down below, now we might draw a dichloromethane like this because it's tetrahedral with those 4 chemical bonds. But tetrahedral is not flat. 2.5 for the carbon, 3.0 for the chlorines, and just 2.1 for the hydrogen. So the carbon to chlorine bonds are polar. And so remember, the molecule is three-dimensional. And if we just rotate that molecule around a little bit, we can see that true angle between those two bonds, an angle of 109.4 degrees. They would only cancel out if they were stretching out on exactly opposite sides of the molecule with a bond angle of 180 degrees. That is not happening. So there's a momentum, angular momentum, sending the electrons down to this bottom pocket of the molecule. We've got a polar molecule again. Two bonds, they'll only cancel each other out if they're on exactly opposite sides of the molecule. And that only happens with two polar bonds when the molecule is linear. Four bonds is tetrahedral. Remember your shapes for the exam next week. Okay, there we go. So we're still seeing polar molecules because there's a majority of electrons or a majority of people on one side of the boat / molecule. Now let's look at some examples where there are polar molecules, but we don't see a polar bond. Carbon dioxide is a good example. We've just kind of talked about this scenario. We've got exactly two polar bonds, and they have got a bond angle of 180 degrees between them. Those bonds are stretching out to exactly opposite sides of the molecule. Definitely a polar bond, of course. 3.5 for oxygen compared to 2.5 for carbon. Remember, you would just be given these electronegativities. You would never have to memorize them. That's too cruel even for me. And so the two bonds stretching, pulling electrons to the two ends of the molecule. But because they're stretching those electrons to exactly opposing directions, it's like a tug of war that ends in a draw. There's no angular momentum. And so the molecule is non-polar. Likewise, when all four of the bonds in a tetrahedral molecule are polar, difference of 1.5 between carbon and fluorine, the 4.0 to 2.5. So all four bonds are polar, and they're pulling to opposing and opposite corners of a cube. So those bonds cancel each other out. There's no polarity to the molecule when all four bonds are polar in a tetrahedral structure. So tetrahedral molecules are non-polar when there's zero polar bonds, and they're not polar when they've got all four bonds being polar. Any other combination, 1, 2, or 3 polar bonds, will make a tetrahedral molecule polar. And lastly, when the molecule is trigonal planar, the molecule is still non-polar if all three of those bonds are polar. So boron 2.1, I think? No, 2.0 for boron. Let's see, 3.0 for chlorine. And so we've got polar covalent bonds between boron and chlorine each time. But our molecule here is trigonal planar. They're stretching out to the opposite corners of the triangle, and they cancel out each other's effect. A 120 degrees angle each time. So it's another example of a molecule with polar bonds, but the molecule itself is not polar. Those bonds cancel out each other's effect. So remember, If the molecule doesn't have any polar bonds, then the molecule is generally non-polar. If it has exactly one bond, which is polar, then the molecule is always polar because electrons are being pulled to just one side of the molecule. The tricky part is when we have multiple polar bonds. Are they working together to draw electrons to one side? That will make a polar molecule. If they're pulling in exactly opposite directions, then they cancel out and we've got a non-polar molecule. That's normally when we've got two polar bonds in a linear molecule, three polar bonds in a trigonoplanar molecule, or four polar bonds in a tetrahedral molecule. They perfectly cancel out each other's effect. Okay, so a little bit left. Let me take a quick check and see what my kids are up to. I hear lots of shouting in the background. So in the next 5 minutes, take a stab at drawing the Lewis structures for hydrogen cyanide, trifluoromethane, and tetrachloroethene. Work out their shape, work out any polarity in the bonds, and work out if the molecules are polar or non-polar, based on the combination of polar and non-polar bonds. So let's take 5. I'll come back and then finish this off, and then we'll be just about done. And we're back. So let's take a look at those examples we had talked about before the break. So first one, hydrogen cyanide, HCN. And of course we can use the periodic table to give us an electron count. For the hydrogen, it's the first element in the first row, so 1 electron. Carbon, of course, 1, 2, 3, 4 boxes, 4 electrons. And the nitrogen, 1 over the 5 electrons. So that's going to give us a total of 10 electrons for this molecule. So 1, 4, and 5, so a total of 10. And for our central atom, hydrogen needs 1 more to make 2, carbon needs 4 more to make 8, and nitrogen needs 3 more to make 8. So carbon should be the central atom. Let me just draw it in black here. So we connect the carbon to the nitrogen and the hydrogen. We'll use the remaining electrons to complete the shells. 2, 4, 6 electrons around the nitrogen. That gives it an octet. But we still don't have that octet for the carbon, just seeing 2 and 2, 4. But we've run out of electrons. So we have to resort to first a double bond to try and solve our problems. So we take a lone pair off the nitrogen, turn it into a bonding pair. That still only gives the carbon 2, 4, 6 electrons. So not there yet. We need another lone pair from the nitrogen. I'll make another bonding pair. Now the carbon sees an octet. 2, 4, 6, 8 electrons. And so, albeit we sometimes break this rule with hypervalent examples, everyone else must have an octet or a duet in the case of hydrogen. So the molecule is finished. No more room for electrons. We've got 2 chemical bonds which get as far away from each other as possible. So the molecule is linear through that carbon atom. Looking at the electronegativities which should be provided with, of course 2.1 for hydrogen, 2.5 for carbon, and 3.0 for nitrogen. So that difference between carbon and nitrogen, 0.5, is significant and therefore makes a polar bond. A dipole arrow runs alongside. pointing to the more electronegative element. It's like somebody asked, where did the electrons go? You're pointing to where the electrons are heading, making this end of the molecule electron enriched together with its lone pair. And so, as we said earlier, with exactly one bond being polar, uncontested by bonds in the other direction, because this is a non-polar bond, the molecule itself is polar. Second one, the trifluoromethane. Let's turn that black, that's better. Of course, 4 electrons for a carbon, 1 for a hydrogen, 7 for each fluorine because it's the 7th element in the row. Leave myself space for the last molecule. That gives us a total of 26. Looking for the central atom, carbon needs 4 more to make an octet. Hydrogen needs 1 more to make a duet. Each fluorine needs 1 more to make its octet. So we expect carbon to make the most chemical bonds. That'll be our central atom. And we'll connect it to the 4 remaining atoms. We've used 2, 4, 6, 8 electrons so far, taking us down to 18. We'll use those remaining electrons to complete the octets, completing the octets of the outer atoms first. And that uses up our electron supply. So that's our final Lewis structure. Carbon has its octet already. It's not one of our hypervalent elements, so we definitely stop at 8. And as we look at the bonds around the carbon, 1, 2, 3, 4 bonds, that's always tetrahedral. So we'll check for those electronegativity differences. Goes hydrogen 2.1, carbon 2.5. Whoop, what happened there? And then finally the fluorine, our most electronegative element, at 4.0. So not significant, the difference in electronegativity between carbon and hydrogen. Remember our range, our target range is 0.5 up to 1.9. 0.4 doesn't cut it. But with 1.5 difference between the carbon and fluorines, we have got 3 polar covalent bonds in this molecule. So they are pulling in slightly opposite directions. Remember, those 3 bonds are like the tripod stand legs of a camera. And they are creating polarity in the molecule. They would only cancel out if all 4 bonds were polar. And they are not. Carbon to hydrogen bond is non-polar. So our second molecule is also an example of a polar molecule. We've got multiple polar bonds, but they do not cancel out. That only happens in tetrahedral when all 4 bonds are polar. Last one, the tetrachloroethene. 4 electrons for each carbon, of course. 7 electrons for each fluorine. So that gives us a grand total of 36. Looking at the central atom, because carbon needs another 4 to make 8. Each chlorine only needs 1 to make 8. So carbon should be the central atom. We'll connect it to the other carbon. And then we can spread those 4 chlorine atoms around the 2 central carbons. That's used 2, 4, 6, 8, 10 electrons so far. So we're down to 26. We'll use the remaining electrons to complete octets. So that's 6 electrons for each of the chlorine atoms. That takes us down to 2. So that last 2 electrons we can put on one of the 2 carbon atoms, doesn't matter which. Don't split them up into individual dots because we never see electrons as paired electrons. If they're filling the shell and filling the orbitals, they're filling with pairs of electrons. Because that does still leave us with a problem for that second carbon because it doesn't have an octet, just 2, 4, 6 electrons. And so does it borrow electrons from one of the chlorines to fill its octet, or does it borrow electrons from the neighboring carbon to fill its octet? Remember, our central atom choice was based on which element needs to make the most bonds, and it's still true that carbon makes the most bonds. So the carbon should be the one supplying the electrons for the chemical bonds. So we turn that lone pair into a bonding pair. Come on. I knew it. I knew it was going to do that. Let's see, let me draw that carbon back in. There we go. So we take that lone pair and we redraw it as a bonding pair. Now we have the octets for each of the carbon atoms, and of course octets for each of the chlorine atoms as well. It's 3 lone pairs and it's 1 bonding pair. So as we look at the molecule, there's 2 atoms jointly at the center, but when we're deciding on shape, we're just looking at one specific point in space. In this case, the carbon on the left with 1, 2, 3 bonds. Same with the carbon on the right, 1, 2, 3 bonds. The chemical bonds here have got nothing to do with this carbon here. It's not connected to them. So with 3 chemical bonds each, it makes the molecule trigonal planar. In reality, 2 trigonal planar jigsaw pieces just join together through the carbons. Looking at the polarity of the chemical bonds, so carbon, that's 2.5, chlorine, it's 3.0. That is significant, that's enough for the bond to be polar. So there's 1 polar bond there, 1 polar bond there, another there, and another there. 4 bonds polar, but all of those bonds are pulling to the 4 opposing corners of a rectangle because of that trigonal planar shape. So they're pulling with equal strength in exactly opposing directions. If you like to say it, the northwest cancelling with the southeast, and the southwest cancelling with the northeast. So it's a molecule with polar bonds, but it's actually a non-polar molecule. Any questions about those 3? Doing okay? It's definitely the trickiest part of the chapter, looking at the polarity of the molecules. You'll recognize polar bonds because there's an electronegativity difference from 0.5 up to 1.9 inclusive. If the molecule doesn't have any polar bonds, then the molecule is non-polar. If it has exactly 1 polar bond, then the molecule is always polar. because the electrons are just being drawn to one side of the molecule. That's all we mean by polar and polarity. There's more electrons on this side, less electrons on the other side. And if there's multiple polar bonds, the molecule will be polar unless the symmetry of the molecule causes those bonds to cancel each other out. There's one last thing to mention, one last piece. Oh, there's a child coming. Yes, baby.
Can you get my hands clean?
I will wash your hands in a second, okay? Go to the bathroom. I'll be there in a second, okay? Okay, stay there. So she's got sticky hands from eating potato chips. Did you enjoy them? Yeah, well, no wonder your hands are sticky. You're sticking your hand down your throat. That's not a good idea. Anyway, so we had talked in the last chapter about compounds being ionic, and we said we could tell they were ionic because normally they would be solids at room temperature, and covalents are opposite. They are normally gases or liquids at room temperature. Now there is some crossover, but if you had to make a guess based on the state of matter, solids tend to be ionic, liquids and gases tend to be covalent. Similarly, when it comes to melting point and boiling point, we said that with a melting point above 400 degrees Celsius, above 400 degrees, that would tend to be ionic. So if the melting temperature is below 400, it's probably covalent. Covalent compounds have low melting temperatures. For the boiling point, if the boiling point is above 1000 degrees Celsius, that's probably ionic. But if the boiling point is below 1000 degrees Celsius, there's a good chance that it's covalent. Again, there's occasionally exceptions, but that would be a good starting point. If it can be dissolved in water or melted into the molten state to conduct electricity, it's probably ionic. If it doesn't conduct electricity, because covalent molecules don't have ions, then it's probably covalent if it doesn't conduct electricity. Okay. If it dissolves in water, as we said in chapter 3, it's ionic. The opposite, not dissolving, would tend to make it covalent. And lastly, if it dissolves in petroleum, main example of that being hexane for your car. If it doesn't dissolve, if it's insoluble in petroleum, then it's probably ionic. But if it does dissolve in petroleum, like hexane, then it's probably covalent. So we're just looking at the other half of the list that we formed in ion chemistry. Covalent compounds tend to have properties which are the opposite of ionic compounds. So if you remember that list from ion chemistry, just remember that covalent compounds normally act in the opposite way. Okay, any questions before we let people disappear for lunch? We okay? All right. Remember, my babysitter is still in quarantine next week. Monday is definitely going to be online again, I'm afraid. Sorry. I'm hoping to have at least one of the 3 lectures next week in person in class. That's always better. But I'll hopefully have more news about that on Monday. Okay? Take care. Wash your hands. Wear that mask.